So we're back, and on this page, we're going to start talking about how to graph a cardioid, or a heart. But first, let's connect back to the first page. Why do I care about understanding or knowing that piece about symmetry? Well, if all you're going to do is fall back on plotting points, symmetry can be very helpful because it will allow you to plot a lot fewer. For example, if I see that I have this equation, it's no longer a circle because there's a number in front of the multiplier times cosine. So this one will not look like a circle, but I can notice that it's a function of cosine. And since it's a function of cosine, I know that I will have symmetry over the polar axis. So the cosine, the fact that it's cosine tells me there is symmetry over the polar axis. And notice I shortened my table of values here. What I can do is I can plot all the points up top, and then because of symmetry, I'll be able to take them and reflect them upside down into the bottom half. And so I can get sort of a 2-for-1 deal here. I can plot half the points and still go all the way around my unit circle. So let's try that. Again, we're just going to plot points. When I plug in 0, right, cosine of 0 is 1, so that would be 3 plus 2. Plugging in 0, I get an r of 5. When I plug in pi over 6, again, what I'm going to do here is put them into my calculator. 2 times the cosine of pi over 6, and I can enter them in and get the decimal. I just can't graph with the exact values. So we're at about 4.73. And likewise, I'm going to go through, I don't want to bore you. You can try typing them all in yourselves and make sure you get the same values. But I don't want the video to be just an hour long of me typing numbers. So these are the values that I got when I typed them in, and now I'm going to go ahead and graph them. In the direction of a 0 radian angle, right, I want to go out 5 units. So that would put my coordinate right here. And in the direction of pi over 6, 4.73. So along that angle, I'm going to go just a little shy of 5. And, I didn't put pi over 4 in here, but let's do it anyways. We've got 3 plus 2 cosine of pi over 4, just because we're new at this. We're still learning how to connect the dots. That puts me at about 4.4. So we'll put it sort of in the middle here. At pi over 3, I should be out 4 units. At pi over 2, I should be out 3 units. At 2 pi over 3, that would be this angle. I'm going to go out 2 units, so 1, 2 on the bullseye there. 5 pi over 6 puts me at 1 1/4 or so. And then when I get to pi, I'm just 1 unit out. Again, we want to sort of connect the dots in the order that we put them, and these are going to come out as nice smooth curves. It's not exactly circles, but I'm going to connect with a nice swirl, just like that. Okay, that gave me about half the graph, and then the trick here is to use symmetry. If I have symmetry over the polar axis, I can take all of those coordinates and flip them upside down. So for example, on 7 pi over 6, I don't need to plug that in. That coordinate here that was at 1.27 is going to reflect down to the same value. 2 pi over 3 was at 2. That's going to reflect down here to 4 pi over 3. Whoops, I missed my coordinate. It should be right about here, 2 units out from the pole. Right, pi over 2, that would reflect onto 3 pi over 2. And pi over 3 was at 4, so that would put me right here when I reflect it over the polar axis. And then this last one, 4.73, just a little shy of 5. And if I think about continuing around the unit circle and plugging those values in, I get this mirror image underneath. So this one has a funny name. It's not a circle. There's a little push, like you just squeezed it in just a little bit. This one is called a dimple, and then it's a French word. It's a limaçon. I'm probably not saying it perfectly with my limited French knowledge, but a dimpled limaçon. Okay, I would not have expected you to know that, but you can plot the points and connect the dots and come up with this curve. Just like with circles, there are some patterns to our cardioid family. So a limaçon is a type of a cardioid, which if you think about cardioid, you've probably heard cardiac before. These graph something like hearts. And the differences between them are minor, but you can get more of a heart shape. This one doesn't have it pushed in quite as far as a heart would be. You can create loops and things. But in general, a cardioid takes this form. Okay? And there is an example right at the top here. You're going to have two constants, an A and a B. You have a constant, plus or minus, doesn't matter. And then there'll be a multiplier times either a cosine or a sine. If you have one of those forms, right, this is a little bit different. Circles would have looked just like that. But if you have a constant in front of that circle, you will end up graphing a cardioid. Cardioids are a little bit more complicated, but they do in general take that same rule as a circle. A positive cosine is going to graph the majority, this bigger part right here, is going to end up on the positive x-axis, right? If there was a negative in front of here, that would put me where the majority, the larger portion of my graph was on the negative x-axis. And likewise, sine, if it was positive, would graph up, and negative sine would graph down. So knowing that, those shapes, it gives me a little bit of assistance. Unfortunately, cardioids have a lot of rules. So if your ratio of A to B, and typically we talk about absolute values here. So I'm not worried about whether this is plus or minus, just, A here is 3, B is 2, ignoring the sign in between. If the ratio of A to B is 1, I will get a true cardioid, and we'll graph one together. It'll look just like a heart. You see these a lot at Valentine's Day with math puns and cards and things. If the ratio of A to B is between 1 and 2, then you will get what we just had above, a dimpled limestone. And another option is that A over B is greater than or equal to 2. Again, I'm talking about absolute values on all of these. So this one is what's called a convex limestone. What happens is that your bubble that's going sort of in, here I'm pushing it in a convex limestone, it pushes out just a little bit, and it looks kind of like a wonky circle. There's another option too. It could be between 0 and 1, and that graphs as a limestone with an inner loop, and we're going to do those on the next page because they're a little bit trickier. But in general, so a couple things to know about cardioids. First of all, it's nice to know that this form means you're going to get one. It gives you an idea of how it's going to graph. A fallback is always just plot a whole lot of points and connect the dots. And if you know that it looks like a cardioid, you'll be able to connect them a little bit better. But there are some cool rules for these guys. One of them is that if you have A plus B, if you take just those values, you will get, or A minus B for that matter, you will get the axis values. These values give the axis values. So for example, if I took 3 plus 2, I would get 5, right? And on the major part, on the larger part of that x-axis, x because it's a cosine, I moved over 5. Essentially, when you're doing the A plus B, you're plugging in the 0 because the cosine of 0 is a 1. And what about the subtraction? Well, 3 minus 2 is 1, and notice how far I went on the negative x-axis, the other part of the x-axis, I went 1 unit over. Essentially, you're plugging in your pi value. The other sort of easy axis values would be A, right? This would gives the other axis. So in a cosine function, what you're doing on the y-axis is essentially you're plugging in a pi over 2 and a 3 pi over 2. But for a cosine function, those would give zeros, and I would only get the A value out because the second term would zero out. So notice I went up 3 and I went down 3 on the y-axis for this cosine function. Right? If I know these sort of tricks, I can make a sketch very quickly and maybe fill in some details by plotting fewer points than an entire chart. So let's try one. On the first one, if I notice, right, it's a 2 and a 2, so I can look at this and know that since 2 over 2 is 1, this one will graph as a true cardioid. It's going to look like a heart. It's going to have symmetry, and because it is a sine function, it will be over the axis theta equals pi over 2. What was our y before? And now we're saying that's theta equals pi over 2. If I take a plus b, 2 plus 2 is 4. Knowing that this is a negative sign, that means I'm going to go on that y-axis. I would go down 4 units. The negative is what's sending me so that the larger value is going to be down, and the sign is telling me that I'm going to plot that on the y-axis. The difference between them, a minus b, would be 0. 2 minus 2 is 0. And so I'm not going to go up on the positive half of that y-axis. If I were to plug in either a 0 or a pi, this whole second term would zero out, and so I would only go 2 to the right, and I would go 2 to the left. And so in general, you could imagine drawing in a heart shape if you knew that this was a cardioid and you had those 4 points. We can be a little bit more detailed. And when I make my chart, the fact that I have symmetry over pi over 2 means that if I graphed 1/2 of that, I could mirror image it and reflect it over into the other half. So I'm going to plot points like 3 pi over 2. I'm going to plot points like 5 pi over 3, or if you want, you can call it negative pi over 3, negative pi over 4, negative pi over 6, and so on. And so I can type those into my calculator rather quickly. It doesn't matter if you're using your grapher right now or your scientific, but make sure you know how to use a scientific later. Negative, pi over 3 would put me at about 3.7, so that's going to be pretty close to my 4. Negative pi over 4, 2 minus 2 sine negative pi over 4, about 3.5, 3.4. If I did it again by plugging in my negative pi over 6, I'm at 3. Right, we already plugged in the 0. That's what gave us our a value. So we can move up to pi over 6. I'm going to cut and paste a little bit here. Pi over 6 is going to give me a 1. Starts to get a little tricky on the inside here. Don't think we need too many more coordinates. Let's try pi over 3. A lot of computation. Right around a quarter, 0.27. So pretty close. And then I'm going to connect this half of my shape with a nice smooth curve in the order that I plotted them. Symmetry tells me that I can take that exact shape and reflect it over. So that little tiny point that was only a quarter of a unit away is going to be on the same side. This one was 1 unit, so that's going to put me over here. Right? The 2 was reflected. Negative pi over 6 is going to be over there. This one was sort of in the middle between 3 and 4, so that's going to be here and here. And I reflected those coordinates, and I can connect the dot. And I get a nice heart shape. The middle one, do me a favor, I didn't realize before I copied, of course, but this was the same one as the one above. So let's just make it a negative. What's going to happen to this particular problem? What is it going to do to make it a negative? Well, it's going to look very, very similar to the one at the very top of the page. If I look at my ratio of 3 to 2, A over B, I notice that that is between 1 and 2, and so this should graph as a dimpled limacone. It is a cosine function, so it will be symmetric over the polar axis. And again, those values would be a plus b. You want to ignore the negatives, so if I just add the numbers, 3 and 2, that's 5, and the difference between them is a 1. 3 minus 2 is 1. So I'm looking at a cosine function, and the larger half is going to be on the negative x-axis. So that means that the 5 would plot here. Essentially, when you plug in pi, you're getting a 3 plus a 2. You're getting that 5. And when you have the 1, so the smaller portion would be on the positive x-axis over here. And likewise, if I were to plug in values that made cosine 0, this whole second term would disappear, and I would have 3, and I would have 3. So again, those 4 coordinates would give me a reasonable idea. If I knew that this one was a dimpled limacone, I could sort of sketch it in. We can plot a few more points to get a little bit better shape because we don't have them memorized very well just yet. Given that I'm symmetric over the polar axis, I'm going to plot the top half and then I'll reflect it into the bottom. So I'm going to plot something like pi over 6, and I would get that value by taking 3 minus 2 cosine of pi over 6. And that puts me at about 1 1/4 or so. So let's see. I'm going to go in that direction, out 1 a little bit more. If I put in pi over 4, 3 minus 2 cosine pi over 4, I'm at about 1.6 or so a little further out when I go in that direction. If I do 3 minus 2 cosines of, let's see, pi over 3 would be my next angle in the unit circle. That's got me at 2. So that would put me right here. And let's see, I already plugged in the pi over 2. We want to plug in, let's see, what would be next? 2 pi over 3. So that's out at 4. In that direction, I'm going out 4 units. And I'm going to do one more. 3 minus 2 cosine of 5 pi over 6 is going to take me at about 4.7. So pretty close to that 5. And I want to think about the order that I plotted them in. And I'm going to connect the dots with that nice curve. I'm going to do mirror images. That one would reflect down here. This one would reflect onto the 4 here. We've already reflected that one when we did the A value. This coordinate at 2 would reflect down to here. At pi over 4, I would reflect right about here and here. And I can keep connecting the dots. So there is that little dimple. It kind of comes in a little bit right at the 0. So I've been talking for a really long time about cardioids. I'm going to go ahead and skip over this last one here. You try it on your own. Pause it, pause the video, see how it goes. I'm going to post a version of this that doesn't have me talking. I'll post just the filled in version and you can check your answer on there. We're going to pause this video, and when we come back with the next one, we'll talk about how to graph cardioids that have inner loops. That's our last topic for the Thursday set of notes if you're out today.